Okay, so we just learned about temperature scales, but we haven't justified why we call to the temperature that we measure with a thermometer, why we call that empirical temperature, and we use a different variable to denote empirical temperature than we use to denote the true thermodynamic temperature. And the reason is that if you have two thermometers, for instance, one mercury thermometer and one alcohol thermometer, and you mark them, or you very carefully make the markings on them according to, for instance, the Celsius scale or the Fahrenheit scale. It doesn't matter. You agree on the same scale for two different thermometers. You apply them to the same system, and they will generally disagree, always, even slightly, but they will disagree. They will only agree at the reference points of that temperature scale, because those reference points are assigned a temperature without error, and any other temperature is inferred from this function that defines the scale. So let me just be consistent and use the same colors. Yes. So this function f of x that we said you could choose it to be some linear function. So simply, if you know what A and B are, because you already calibrated your thermometer, whatever volume you measure, you put it in there, and you calculate by extrapolation what is the corresponding empirical temperature. And unless this happens to be one of these special reference points, the empirical temperature will carry some uncertainty, and in general, empirical temperature of different thermometers won't agree. So from a fundamental point of view, it's very dissatisfactory that you have a physical property that you know it exists, but you cannot really measure it reliably. So this is why we call anything you measure with a thermometer empirical temperature. And all we need to do is to find a thermometer that we all like. And from now on, we have to stick to a specific thermometric scale and a specific type of thermometer, so that we can all compare our measurements with one another. Okay, and we are going to take by convention the gas thermometer at constant volume, and we are going to express the temperature in Kelvin. Okay, so if we do these two things, then we claim that what we are measuring is not empirical temperature anymore, but it's actually true thermodynamic temperature. Okay, so again, as a working definition of the true thermodynamic temperature is the empirical temperature measured with a gas thermometer at constant volume expressed in Kelvin. Okay, we are of course going to justify this later, but before we do that, we need to introduce Carnot's theorem and heat engines, the ideal gas, and we also need to introduce internal energy and heat. So it's still a long way from us, but we are going to justify this. And the reason why we choose the gas thermometer at constant volume is that even if it's specific type of thermometer, it does seem that different gas thermometers made of different gases tend to agree in their temperature readings on a same system, even if they are made of different gases. And it means there's something universal about those thermometers. And let me just explain what the gas thermometer does. I'm going to try to make a decent picture here. So here is a bulb, and this bulb is filled with a gas. And this gas is very rarefied. But like I told you, it could be anything. It could be air, it could be hydrogen, it could be oxygen, it could really be any gas, as long as the density is sufficiently low, the pressure is sufficiently low. And then, well, there is a capillary tube here. Let me just try to make a good picture. And there is a tube like this in the shape of a U. And, okay, let me try to make it nice. Okay, like this, and this continues, okay, up. And then here there is an opening, and in this opening I have another thing that goes to a deposit. And this whole thing, these whole tubes and the deposit up here is filled with mercury. Okay, So what happens is that, okay, this is not nicely drawn. Okay, so here I have a bunch of mercury, and this mercury is filling this tube, and it's also filling here and there. So if I don't know, bring a flame to my thermometer here, then I will increase the temperature of this gas, right? And then, so actually this is what I use to measure temperature. Let's not put a flame, let's just say we submerge the bulb of the thermometer in whatever system whose temperature we want to know. So if the system is warm, say it has a higher temperature, then what will happen is that the pressure of this gas is going to raise. This is something we know from empirical experience, no? So observations. And what will happen is that this gas will try to push a little bit the mercury, a tiny little bit. So what we do then is we try to move this thing up and down in such a way that, well, this is, like I told you, open, it's connected to the atmosphere, and we're going to try to move this thing in such a way that we can push this mercury all the way back up, and we keep the volume of the bulb that is available to the gas constant, because we are really shutting it with the mercury. The mercury is the stopping point of the gas. And once we've done that, the level of the central column here of mercury is going to change. And we are going to be able to measure that difference in height very accurately. Okay? And from this difference in the height, we infer the temperature. And what I'm telling you is that at this stage is still empirical temperature. What I'm telling you is that if you express that empirical temperature in Kelvin, you can call it capital T. It's actually the true thermodynamic temperature. And the point here is that if you fill this with hydrogen or with oxygen or with anything you like, with air, which is a mixture of different gases, you certainly measure the same empirical temperature or the same temperature for the same physical system, which means there's something universal about this setup, and that's why we choose it. Okay, so then this is everything I really wanted to tell you about thermometry, temperature scales, and so on. Now let me close this first topic by making some definitions, okay? So first of all, remember the mug of coffee, which I already finished long time ago, but the thing is, remember, why was the coffee cooling down? It was cooling down because it's open, the mug, right? And if I, for instance, had one of these fancy insulated takeaway coffee mugs, the coffee, I know that it will remain warm for a much longer period of time. I know that eventually it will get colder and colder, but it may last up to a few hours being very warm and nice to drink. So if you have a system that is contained in boundaries or walls that are insulating, it means that the temperature of your system, yes, even if you have a different temperature outside, the temperature of your system is going to remain roughly constant for a long period of time. If you have a perfect insulator, which is an idealization, it doesn't exist such a perfect insulator, but if you could have, in the limit of perfect thermal insulation, the temperature of your system will never change, even if outside the temperature is much lower or much higher. Yes, so this system inside of such perfectly insulating wall is not in thermal contact with the outer world. Okay, and this type of wall is called adiabatic. Okay. So when a system has adiabatic boundaries, they are perfectly insulated. It means the system is thermally insulated from the outside. It's not in thermal contact with the outside. And just by opposition, right, when you have a system which is in thermal contact with the outside and whose temperature is changing when I change the conditions outside, when I put it in contact with another system, then I say that the walls are, in this case, where the temperature is changing, so I don't put anything. In this case, the walls are diathermal. Okay? So diathermal wall is a wall that is not perfectly insulated, and it means that the temperature of my system is going to change depending on what's the surrounding conditions. Yes, and this is going to allow us to define heat from an operational point of view. So we are not physically going to define heat yet. We're going to do that in 2 chapters time. But imagine that you have the following system, okay, which is a calorimeter. So it's like a box, and this box has adiabatic walls, so perfectly insulating walls like this, okay. And in this system you have a known amount of water, so this is all full of water, so maybe 1 kilogram of water or something like this, a fixed mass that you know what it is. The water here is called calorimetric water. Calorimetric water. The walls, I told you, are adiabatic. And here you have a thermometer. Okay, so there is a thermometer here that you can use to measure temperature. Ideally, it should be a gas thermometer, but okay, let's just write this thermometer. And here you have your system. Okay, and something is happening to your system. So as a result of that something that happens to your system, you see that the temperature of your thermometer goes from 14.5 degrees Celsius to 15.5 degrees Celsius. Okay, so if this happens with a kilogram of water in your calorimetric water, then you say that this system inside of the water has released into the water 1 kilocalorie of heat. Okay, I'm not telling you what heat is, I'm just telling you how you measure it, in which units can you measure it. On the contrary, if I have the reverse process in which my temperature of my calorimetric water goes down by 1 degree Celsius, then I claim that the system has absorbed 1 kilocalorie of heat. Okay, so just by checking the changes in the temperature of the calorimetric water, I can tell whether a system inside of my calorimeter has released or absorbed heat, and I can actually quantify which amount of heat, because I can accurately quantify changes in temperature, and I know very well, accurately as well, how much water I have here. So without defining what heat is, I'm giving you a sense of what it is. And another way of speaking about adiabatic walls is adiabatic walls are those boundaries through which heat cannot be exchanged. So if a system is perfectly insulated, it will never release any heat to the outside. In particular, if these boundaries of this system were adiabatic, I would never see any change in the temperature of my calorimetric water. And on the contrary, diathermal walls are walls that allow heat to flow through. So that is the last concept I wanted to mention in this chapter, and I will see you in the next chapter about the ideal gas.